Back to the next episode of Blind75 LeetCode problem. Today we are looking at the 10th problem, which is search in a rotated sorted array. Okay, so the problem states we are given an integer array nums which is sorted. Prior to being passed to the function, it is possibly rotated. That means it might not be rotated, it can also be rotated. So either one of this, okay? And at an unknown pivot index. Uh, then we are also given a target and we have to find out whether the target is in the rotated sorted array. Okay, let's look at the constraint. So the number, the nums is at least, the length of the nums is at least 1. So you don't need to handle the empty list use case. And each number can be can vary from minus 10 to the power 4 to 10 to the power 4. All values are unique in the nums, and it is an ascending array, which is that is possibly rotated. Okay, and the target is also in this particular range. And the problem also states that we have to write an algorithm with order of log n runtime complexity. Okay, so given this is kind of clear that we should use binary search. That is where we search for a target in a sorted array and divide the search space by 2 every time. That's why it becomes order of log n. Okay, so let's look at how to solve it, right? So I have written the same array rotated at different pivot indexes. So if you look at the first one, it is an ascending order, not rotated. And this is another one where we are rotated at pivot index 7. So yeah, this is how the graph looks like. It increases and decreases, then increases, right? So similarly, the last one is rotated on the first half of the um, array. The second one is rotated in the second half or in the middle. Okay, so it can also be something like say I'll write another example: 2, 4, 5, 6, 7, 0 and 1. So here it is more like here, and so this is rotated at the second half of the array, this is rotated at the first half of the array, this is in the middle, and this is not rotated at all. These are the possibilities. Okay, how can we solve this? So order of log n, so we have to do binary search, right? So what can we do? So we can find the pivot index, like wherever this is being rotated. For example, in this one, the biggest element is at the end, so that is where it is rotated. It's not rotated, kind of. So here we have to find this area. Basically we have to find the biggest element, and where the biggest element lies in the array. So that's the pivot index. So we can do this by doing a binary search, and we can find the pivot index. And once we know the pivot index, what we can do is we can search in the binary search way with dividing that array into 2. For example, once we find this position, we can check for the target in this range and this range. Here we can, so we will find this particular pivot index, which is the highest number in the array. Then we can search here and we can search here. So 2 binary searches. If this is the case, we can search in this array, this sub array, and this here. Here we will search from here because it's not rotated. Okay, so this is how we can solve it. How do we find the pivot index, right? So we can use something like similar way where we find the middle element and we'll check. So if I had to take an example, let's take a look at say, yeah, the second array. um, yeah, 4, 5, 6, 7, 0, 1 and 2. What is the middle element? Here the middle element is going to be 7. Okay, what we will do is, whether is the mid element greater than the last element. Is it greater than the last element? Yes. So where should we search? That means there could be bigger numbers here. So we will keep our searching space from here. So we will set left as mid plus 1, like we will set left as mid plus 1 until the right element. If it is not, so let's take a look at another example. What if it is rotated in the first half, right? So 0, 1, 2, 4, 5. What is the mid element initially? So it would be 1. Is 1 greater than 5? No. That means the rotation or the pivot index is on the left. So we will keep searching on the left. We will not search here. Okay, we will keep searching in the first half. So like that. Then when it ends, we will be at the pivot index. Okay, and once we know the pivot index, we can do 2 binary searches to find whether the target exists in the binary search or not. For example, we'll search here and we will search here. If this was the array, we'll search in this particular subarray and this particular subarray. Hope this is clear. Let's go ahead and implement this solution. Okay, so let's get the length of the nums, which is n, and we will say left comma right is equal to 0 and n minus 1, where these are the indices, and we will run a loop similar to binary search, and mid is going to be left plus right divided by 2 if nums of mid greater than nums of minus 1. Nums of minus 1 is the last element in the. So in that case, we will start searching from the second half. That is, we'll set the left as mid plus 1 so that it searches on the second half of the, or the right side of the mid. Else we will have to search on the left side. So we'll keep right as mid minus 1. Okay. So at the end, we will have pivot index at the left position, right? So let's write the binary search problem. Okay, so what we have is L, R and target. Then we'll do left is okay. I'll write differently here so that we don't get confused with variable names. So yeah, L boundary, R boundary. So L is equal to L comma R is equal to L boundary comma R boundary, while L less than R, mid is equal to L middle index is equal to L plus R divided by 2. If nums of mid equal to target, return mid. We will return the index where the target exists. L if nums of mid, if the mid is greater than target, right is equal to mid minus 1. Else left is equal to mid plus 1. If return minus 1. Okay, that means we didn't find it in that particular array. Okay, so now from this code we got the pivot index, which is left. So what should we do? Okay, so let's check in that left index. If binary search of starts with 0 and left is the pivot index, right? It can in the previous example it will be where the 0 exists, so we will search until that particular index. So left minus 1 and target equal not equal to -1, that means we have found the uh, answer. So okay, so in order to avoid keep calling this again, I'm going to assign this result, right? Result is equal to binary search of target. I'm assigning when we are calling. Then if it is not -1, that means we have found it, so we don't need to return it, right? So return the result. Otherwise what we'll do, we'll return binary search of left and -1. So we'll search on the right half. Okay, so let's see how yeah, if this passes. Seems like it's taking a lot of time. Let's revisit our okay, solution and see if we missed anything. Okay, sorry, we have to, this is the mistake I did. Okay, so we are assigning L here and R, and yeah, let's try running. Let's see, 0 to left -1, target not equal to -1, return result, left and -1 and target. Okay, what is wrong? N is equal to length of num, left comma right is equal to 0 to n -1. Okay, let's debug this. Okay, for now I'll just return left, so that so that it doesn't raise an error. I'm going to see if we are able to find the okay. Let's take this particular example. Okay, case 1. So we got 4, which is 0, 1, 2, 3, 4. So we got this 0 index wherever the smallest element is. Okay, that is fine. And let's see this. So we have the left, then okay. Okay, so the problem is in the second half of the solution. Okay, let's take a look. In the binary search, we have left boundary, right boundary, and the target, and we are doing LR as L boundary, R boundary, then mid is equal to okay, yeah, we missed an equal value. Okay, let's see, mid is equal to left plus right, here by 2, left of norm is equal to target. So of mid, if it is greater than target, we will, oh, okay, yeah, right and left is equal to mid plus mid. Okay, let's see. Yeah, we were doing this solution wrong. Okay, let's see. Ah, there you go. Okay, so ideally what we missed was this equal to condition and the, yeah, so if the mid is mid element, for example here, if it is greater than target, we have to start searching in the first half, like, yeah, until mid. So we set the right as mid minus 1 and go ahead and do it on the left side. Otherwise we check it on the right side, where left will be starting from 0 to the end of the array. Okay, yeah, there you go. So we got this. What is the complexity here? So this is order of log n and this is order of log n, but we might be doing it 3 times, right? First to find the pivot index, second to find it in the first half until the pivot index, and if it is not found, we'll check in the second half. So in the worst case, it would be order of log n plus order of log n plus order of log n. So we can say it is order of log n. Okay. So can we improve this? Yeah. So instead of doing it 3 times, we can do it in a single iteration. How can we do it, right? We still will go through the binary search, but we will depend on the first value or the second value, like the, yeah, first value or the second value, to find out whether which area to search, like how to shrink the space while searching. To give you an example, okay, let's take this example, right? 4, 5, 6, 7, 0, 1, 2. Okay, so here this is the mid element, right? If the mid element is greater than the left element, this is greater, right? Then we can check whether the target value, for example, the target is 6 here, so we can check whether it lies in this area. If target is less than or equal to 4 and greater than or equal to 4 or less than or equal to 7, then we'll go ahead and search here. Okay, otherwise we'll go ahead and search here. What would happen if in the else case, for example, let's take the other example, 6, 7, 0, 1, 2, 4, 5. So what is the mid element here? Mid element is 1. Okay, is target, so we have to find out whether the value is here. So in the else case, if target in this case is say 6, right? If 6 is less than or equal to nums of right, so here the right is 5, right? If target is less than 5 and target is greater than mid, so that means it lies in this particular area, 2, 4, 5. So we'll search here. If it is not, if in this case 6 was the target, is it lies in this particular value? Is it if it, suppose the target is t, so is it 1 less than or equal to t less than or equal to 5? No, right? So then we'll go ahead and search on the first half. So this is how we can reduce the search space and keep it as order of log n. So instead of doing it 3 times here, we are reducing it, and let me submit this and then we'll come back and okay, let's solve this in a single pass. Okay, so this is same, then we'll write the loop, right? mid, what is mid index, which is left plus right divided by 2. If nums of mid equal to target, that means yeah, we have found it, then we'll return it. Okay, so we'll write this write the conditions that we wrote. Nums of mid, if nums of mid is greater than or equal to nums of target. So the element in the middle is greater than nums of left. Okay, then we have two conditions. We have to check whether it lies in this particular first half until the mid or in the second half, right? So how do we check it? So we'll check if target greater than or equal to nums of left and target less than nums of mid. Then we have to search in the first half. So we'll set it as right equal to mid minus 1. We have to search from left to the mid minus 1. This is example. So this is the mid and the target is say 6. We are checking whether 6 is in between this value, like 4 less than or equal to t, which is target, and less than 7. If that is the case, we'll search from here to here. We don't need to include 7 because we have already compared whether it is a target, right? So we'll check for the subarray this. Okay, so we'll set it as right equal to mid minus 1. Else case, we'll set it as left equal to mid plus 1. In the other case, we'll look at the right. And the yeah, so the next else is in a case like this where the mid element is a smaller value. So we have to check whether it lies in this particular not including mid, whether it lies on the right subarray. So what we'll do is, if target is less than or equal to nums of right and target is greater than nums of mid, then what we'll do is left is equal, we have to start searching from the mid plus 1 until the right. Else case, we'll do right is equal to mid minus 1. Then we'll if you have reached here, that means we haven't found anything, so we'll return minus 1. So just to clarify this, we are checking whether the target is in between, like if the target is less than or equal to, like whether it is less than or equal to 5 and target is greater than 1, that means it would lie in this area. Okay, so let's try running this. Okay, yeah, so what is the complexity here? So we are doing the iteration order of log n times, because every time we are dividing the search space by half, right? So for example, we check here, then we'll divide it into half. So instead of checking in the whole array, we divide it in the first half, and here we will again check the mid element and then go to either left or right based on the scenario. So we so we kind of divide it. So this is just order of log n. Let's try submitting it and see if we missed any test cases. Okay, so this is passed. So that is the end of the 10th problem, search in a rotator sorted array. Thanks everyone for watching, and if you have any comments, please let me know, and yeah, any feedbacks are welcome, and see you in another video soon. Thank you so much for watching. Bye.